Hello, Calc 2 students. This is the first of about 8 videos of about 15 minutes each to replace the 2 hours of instruction next Monday, where on the 15th of November, when I won't be there, as we talked about. So picking up from where we left off in lecture on Wednesday the 10th, talking about the geometric series and the nth term test for divergence. We had discussed the geometric series proof that this series, the summation a times r to the n, as n goes from 0 to infinity, is convergent if r, the ratio in absolute value, is strictly less than 1, and divergent if r in absolute value is strictly greater than or equal to 1. So, for example, if r is equal to -1, that would fall in this category, or r equal to 1. And this is an open interval of fractions between -1 and 1. If it does converge, it converges to a over 1 minus r, as we proved in class. So here's an example of using it. It's kind of interesting. What is the number 0.99 repeated actually equal to? You can use geometric series to evaluate that. And since 0.99 repeated is the same thing as 0.99 with infinitely many nines here, and that is equal to 0.99 plus 0.0099 plus 0.4099 plus, and so on and so forth, infinitely. And we can factor out a 0.99 there. That leaves 1 plus 100th plus that 100th squared, plus and so on. In other words, if r is equal to 100th, then 0.99 is multiplied by this geometric series. And since r is equal to 100th and a is equal to 1, it will converge to a over 1 minus r with those values. And what does that give us? Well, that 0.99 that was factored out still there. A over 1 minus r is 1 minus 1 minus r, which was 100th, and that is equal to 0.99, that constant out there, over 1 divided by 0.99, or 99 100ths. So 99 100ths times the reciprocal of 99 100ths, or 100 over 99, those cancel out, and we're left with 1. So therefore, if you see 0.99999, infinite number of nines, that is the same thing as the number 1. Now you try it. Your first question on the assignment that I gave you, which was to view these videos, and where there are given questions, note that what the questions are on a piece of paper, work out their solution, take a picture of that, and at the end of all these videos, you'll have some number of problems, and you will attach those pictures to an email or emails and send them in to me by the end of the day on Monday the 15th for a quiz grade. Okay. So example 2 of using the geometric series. Whereas the previous example, we were looking at 0.99 as a ratio, now, which is 1 minus 100th. What if we had 1 plus even something smaller than 100th, say 100th divided by 5 times 10 to the 200? Okay, huge denominator there, making this little quantity here very tiny, but that makes a ratio r that is ever so slightly greater than 1. And therefore, by the geometric series theorem 9.6, it diverges. If it's divergent, then you don't have to find what it diverges to. It's just divergent. Example 3. Our example 3 is actually problem 32 in section 9.2. It is an example of looking at a telescoping sum. That doesn't look much like a telescoping sum, but if you use partial fractions, as I'm doing here to remind you what that process is like, you end up getting that this rational function, 1 over 2n plus 1 times 2n plus 3, can be split into the sum of two rational functions, or the difference. See that negative there? And here I was just checking my work that these a and b values do work. Continuing. With that example, which again is problem 32 of section 9.2. It's on page 605. So now, because of the partial fraction work, I can see that this is a difference, and leaving me hope for looking at this as a telescoping sum. If we factor out the 1/2 and we expand this summation here, you can see that we have, well, 2n plus 1 is how you refer to an odd number, and 2n plus 3 would just be the odd number after that. So starting with n equal to 1, we end up having here 1/3 minus 1/5 plus 1/5 minus 1/5 plus 1/7 minus 1/7, and so on. These can be regrouped in this way, all these sums being equal to 0. So this is a telescoping sum. Using the notation of the book, the nth partial sum of a telescoping sum of this form, b1 minus b2 plus b2 minus b3 plus b3 minus b4, if that's the form of the telescoping sum, the nth partial sum is b1 minus bn plus 1. All those other minus b2 plus b2 minus b3 plus b3, all the intermediary terms disappearing, telescoping into this small quantity. So here our b1 is 1/3, b2 is 1/5, b3 is 1/7, and so on. Bn is 1 over 2n plus 1, and bn plus 1 is 1 over 2n plus 3. So therefore, the nth partial sum is b1 minus bn plus 1, or 1/3 minus 1 over 2n plus 3. Remember, I said it was very handy to have a formula for the nth partial sum, because then when you take the limit of that, you get the actual value of the series. Okay, now this series is S, where we had factored out the 1/2, and so I'm just looking at this as my series, infinite series S. And by taking the limit of its nth partial sum, we see that that series S is 1/3. Now, that means our problem that we started with, which is 1/2 times S, is 1/2 times 1/3, or 1/6. Here's your second question for your quiz grade on Monday. Find the sum of this series. We also had discussed the nth term test for divergence on Wednesday, November 10th. That's theorem 9.8, by the way. It's on page 603 of section 9.2. It says that if a series is convergent, a series of terms summing up the a sub n's, if that converges into some definite number, then the limit of the nth term has to be 0. Here's that proof I promised you. Well, let's assume that this limit of a sub n as n goes to infinity is equal to some k. What we're going to do is show that that k has to be a 0. So if we suppose that the series, which we were told is convergent, converges to L, some finite number, notice that that says the limit of the nth partial sum is equal to L. As I've been saying, that limit of S sub n, the nth partial sum, is the definition of an infinite series. And note also that the limit of S sub n minus 1, even if you only gathered the first n minus 1 terms of the series and call it S sub n minus 1, well, and then you take a limit as n goes to infinity. That's going to be the same as the limit of S sub n as n goes to infinity. So this is also equal to L. However, the nth partial sum is equal to the n minus 1th partial sum plus one more term, right? S sub n is all the terms from the first to the nth. If this is the nth term, you add that to the sum of the first n minus 1 terms. Oh, that's S of n. That's an equality. Take a limit of both sides as n goes to infinity. The limit of S sub n is, of course, L, but the limit of S sub n minus 1 is also L. The limit of A sub n is what we were calling K. So K has to be some number that satisfies this for no matter what series. For the series of no matter what, but the series of adding up the A sub n's. So L is equal to L plus K. That is only true if K is equal to 0. QED. So I'm concluding this first video. This is page 5 of video 1 by looking at an example of using the nth term test. The example I'm using is actually working problem 46, page 605. The summation of 6 to the n over n plus 1 is the series, and therefore the nth term is 6 to the n over n plus 1. If we want to use the nth term test for divergence, we take the limit of the nth term and see what we get. What is the limit of this nth term? If it exists, by the way, it has to equal to whatever the limit is of 6 to the x over x plus 1 as x goes to infinity. Remember, we're considering some function here where if you evaluated it only positive integers, you would get a sub n. Well, notice that the limit of 6 to the x over x plus 1 as x goes to infinity is an infinity over infinity type limit to which we would apply L'Hopital's theorem. And you can check that the conditions are satisfied. And the limit of that ratio of 6 to the x over x plus 1 by L'Hopital's rule is equal to the limit of the derivatives of each of those in ratio. And since the derivative of x plus 1 is 1, we're just now looking at the limit of 6 to the x times some constant. 6 to the x is certainly going to plus infinity. So therefore, the limit of a sub n, 6 to the n over n plus 1, is also going to go to the same limit, plus infinity. That's certainly not 0. So by the contrapositive of the nth term test, theorem 9.9 is the book's statement of the contrapositive. Since the limit of the nth term is not equal to 0, therefore the series summation of a sub n terms from 0 to infinity does not converge. In other words, it diverges. Okay, so your third question for your assignment on Monday is to do problem 48, section 9.2, page 605.